have a colloquium today. Today we're very happy to have speaking to us John Conway from the University of Princeton, known for a great many things throughout mathematics, but today what he'll be talking about is the remarkable history of Pascal's hexagrammum mysticum. I'll let John explain what that means.
Thank you, Jason, but the first thing I want to say is anybody really interested in the remarkable history of
How can we answer? We don't know what it is.
Let me give you a hint. The correct answer is
Can I switch places with you? Actually, could you sit here?
Because I propose instead to talk about something totally different. And actually I have a history of talking about this totally different thing on other occasions too. This is the talk that I actually gave at the 1994 International Congress in Zurich, and I was set to give a talk on developments in the last 4 years in sphere packing. And they have a habit of doing this. You know, they think it's been 4 years since the last Congress, so you want to be updated in X theory and Y theory and everything else. But to my mind, that really means give a boring talk in which nobody is interested. And just the week before, I had attended a conference on games. By the way, the year before, I'd attempted suicide. Not that that's any of your business, but I'll tell you about it. Well, no, I mean, I'm just telling you the fact. I was terribly depressed. Nothing to do with mathematics, you know, as usual. I was still suffering from clinical depression at the time of the Zurich Congress. And as you may know, one of the well-known symptoms of clinical depression is that you can't sleep, insomnia. You know, I was sleeping an hour a night if I was lucky. And this is really the talk that brought me back to life. So what happened was, the week before, I was quite worried about what to talk about at Zurich, or at least, you know, how to make anything about sphere packing interesting, or anything. And the week before, I attended a conference on games at Berkeley, hosted by my friend Elwin Berlekamp. And I gave a talk on that. And I telephoned my wife. You know, she said, how did the talk go? That's what wives are supposed to do. One of the things wives are supposed to do. And I said it was a disaster. And, well, every now and then, you know, I'm such a good speaker. Every now and then, my standards are so high, you know, that every now and then I telephoned my wife, you know, and said it's a disaster, and then had somebody coming up to me and saying that talk was the best talk I've ever heard in my whole life. And I kid you not, that's really happened a few times. So, how can I say it? I didn't know whether to trust my opinion that it was a disaster. Maybe the other people thought it was okay, you know. Probably some of them did. But then I got better evidence a day or two later, when Richard Guy was chairman of a session, and he said, one of the speakers hasn't turned up, can you give a talk? Well, I said, yes, of course, because that's what I always said, and I'd lose face if I ever said, no, I can't give a talk. Yes, of course. When? He said, now. This was the nowest now. You can conceivably imagine. Imagine we were standing having this conversation at that door. Well, it was actually a door in the middle of the room. And I had just the time it takes to walk down the aisle to decide what to give the talk about. And I thought, I must make it a golden oldie that I've given lots of times before, and it's always been successful. And I have that thought today, you know. I was interested in Pascal's theorem at the time I gave this title. I'm still interested in a sense, but my interest is in abeyance at the moment. Anyway, I thought I must give a go of the novelty. Let me see, what can it be about? And I thought, well, I thought I'll give the lexico talk. You won't know what the hell that means, I hope. I hope if any of you have heard it before, you will keep your big mouths shut. Or your dainty little, very pretty mouths. I mean, I don't care what shape your mouth is. Shut up. So what was this talk about? Well, it's rather strange. Oh, look. Here, I carefully prepared this. Can we see it? Yes, we can. This is the start of the integral lexicographic code of minimal distance 3. So a code word is a string of things I'll call digits, but the digits are really arbitrary non-negative integers. I won't often have occasion to mention digits bigger than 9, so you can sort of basically think of them as if they were the decimal expressions of numbers, but really they're not. Lexicographic, it means, well, integral means that, you know, that the digits are integers. Lexicographic means, well, the same sort of lexicographic order as the usual decimal representations of integers satisfy. So, for instance, these are, well, apart from the leading one, they're all 3-digit numbers. Let me just think of them as numbers for the moment. And they're in the order you think they are. Now, well, they're really determined by what is nowadays called the greedy algorithm. I prefer to call it the lexicographic condition, but anyway. Each word, I'll call these things words, is to be the earliest possible word that differs from each of its predecessors in at least 3 digits. Okay? There's no choice. It's got to be the earliest one. So, let me sort of cover up everything. What word are we going to write as the very first word of all? It's got to differ from all its predecessors. Oh, it hasn't got any predecessors. So whatever we're going to say, that's no condition. It must be the earliest possible word of all, which is that one. Now, what's the earliest word that differs from that in at least 3 digits? Well, it's got to have 3 ones in it. Sorry, if they're not ones, there's an earlier one that does have ones. And if it's got more than 3 ones, there's an earlier word with 3 ones. And if the 3 ones are anywhere but at the end, then this word beats it. So that's the next word. Okay, well, I think you can follow the next few words. N, N, N. I'll suppress leading zeros the way we usually do for decimal numbers. N, N, N is in the lexicode. Oh, this is C3, by the way, which means the integral lexicode of minimal distance 3. And now, what's the one that, now the interesting thing in this is that this induction is really a transfinite induction, but don't be frightened by that. It just carries on after this. Take all of those words as given to us, infinitely many. What's the next word? Well, I'm glad you asked. Very sensible question, congratulations. It is, well, it's got to stick out into the 4th place from the end, and if it's the earliest one it can be, it'll stick out with a 1. And then, well, let me write it up here somewhere. There seems to be lots of coloured chalk, but no...
To your right-hand side is
On the wall.
on the wall is white, and behind you, right there, in a little white.
Oh, same as right?
No.
Oh, right, it's on the left. Okay, fine. Okay, I'm sorry. I'm deaf and dumb in front of an audience, roughly speaking. Okay, so what is this word? A, B, C. Well, so A, B, and C have to be different integers. By the way, I'll use integer for non-negative integer. A, B, and C have to be different because if, say, two of them were the same, then this would differ from the earlier word A, in only whatever it is, digits. And it's got to differ in at least 3. So they've got to be different. And so what's the earliest choice of 3 different integers? It's not 1, 2. Okay. So the next word, the first word after all of those is 0, 1. 1, 0, 1, 2. And then comes 1, 1, 0, 3. I could justify that, I suppose, and maybe I should. So I will. Maybe I shouldn't. But that's simple then. 1. We can't have a 0 here, because then it differs from this word in at most 2 digits. So it must be at least a 1. Let's try whether there is one with 1. Now, what about this next one? Well, I don't see anything wrong with it being a 0. So I'll tentatively try a 0, because 0 is the least possibility. Now, can I have a 0 here? No, because then it differs from the all zeros word in only 2 digits. Let me just say it's too close to the all zeros word. Can it be a 1? No, because then it's too close to the 111 word. Can it be a 2? No, because it's too close to this word. Can it be a 3? Well, I don't see anything wrong with that. Let me prove it's a 3, in fact. Let me prove that it can be a 3. Because these 3 digits are different, it differs from all those NNN things. And we've just checked, it differs from this in 3 places. So it can be that, and therefore it must be that. And then the next one turns out to be 1, 2. I won't bother to justify these things. And now an interesting thing happens. If in any other word of this shape, in this word, every digit must be 4 or more. It's easy to see that because we've had 0, 1, 2 and 3 in every position in the last 4 words. So it's just, when we're choosing this next word, it's just as if the integers began at 4. We're not allowed to use 0, 1, 2 or 3, and the argument's exactly the same. So we get 1, 4, 5, 6, and I'm just repeating these now with these numbers increased by 4. Well, I'm not going to go on justifying it anymore. I will say, can you see it over? Yes. I will say that the first word that begins with a 2 is 2, 0, 2, 3. And the first word that sticks out into the 5th place is 1, 0, 1, 2, 3. And that, I think, is all I'll need to illustrate the theorem. And the theorem is a rather strange theorem. It's a very good theorem. And I call it the lexico I like the idea of writing theorem in capital letters because I'm rather proud of it. And it says, under the natural coordinate-wise, coordinate's an awfully long word. Definitions of vector addition and scalar multiplication. All lexicodes are vector spaces. Now, why hasn't somebody complained yet? Okay, well, never mind, you've accepted that. Fine. So, what that means is, of course, that they're closed under coordinate-wise vector addition and scalar multiplication. So, let's take some of these words and check. Well, I really checked in a way that, you know, here's one word. Well, look, let me give you a very simple example. Let's take 0, 0, you know, 2, 2, 2, and 0, 0, 3, 3, 3. I mean, both of these are in C3, and the answer is 0, 0, 5, 5, 5. Well, of course, I chose an easy example. That should be in C3, and indeed it is. Let's take another one. Well, let's take 0, let's take this one here, and then 0, 1, 0, 1, 2, and add them up, and we get 0, 1, 2, 3. That can't be right. 4. Yes. Well, that doesn't appear to be there. And in fact, we can prove it isn't there. Let's say, let me say should be, according to the lexicode theorem, should be in C3. But 0, 1, 2, 3, 0 is in C3. And they differ in less than 3 digits and more than 0 digits. And therefore, there's something wrong with this. And so we've got to edit this somehow so that it becomes true. And perhaps the simplest edit is to call it the lexicode none. And that's perfectly satisfactory, that's okay. But let's look at it again. Oh, yeah, you know, I'm sorry. I think I said denatural. I shouldn't really have done that. That was a mistake, a genuine mistake on my part. Is there any way we can sort of rescue this theorem so that it becomes true? Well, let's try. I tell you what. Let's edit it. Are there coordinate definitions under which all lexicodes are vector spaces. Oh, it's no longer, this is a good name, so I'll call it the lexicode problem. Okay. So now let's tentatively suppose that there are. And then in particular, here's a word, it's the all zeros word, plus the all zeros word ought to be in the code, whatever it is. However, I'm not quite sure that 0 plus 0 is 0. So let it be Z instead. And then let's say this is in C3 and this is in C3. So this word Z, 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 or whatever it is, I seem to have put fewer Z's than I thought, should be in C3. Okay, but the way I defined the lexicode, it's clear that every member of the lexicode begins with an infinite string of zeros. I think I said that explicitly. If I didn't, I should have done. Therefore, Z equals 0, i.e. 0 plus 0 is 0. So that's a theorem, and it deserves a name, and I'm going to call it theorem 0. 0 plus 0 is 0. And now we've got a start. Here's the addition table. We've got a long way to go, of course, but we have at least filled in that entry, if the theorem is to be true. Oh, but look, how can I say it? If, just let me remark, if x plus x equals x in a field, then you add minus x to both sides, or whatever, and you'll get that x is the 0 of the field. So i.e. n plus 0 equals n equals 0 plus n for all n in the field. By the way, none of you noticed, maybe you took the instruction to keep your big mouths shut too seriously. None of you seem to notice that fields are usually, so that vector spaces are usually defined over fields. And so I should have said two-dimensional Z module or something before. But then I got that past you, so that was okay. So we have actually got a lot more entries in the addition table of our field, as it will turn out to be. What's 1 plus 1? Well, once again, I'm glad you asked. You don't seem to be asking the most intelligent questions, even if you don't come up with the most intelligent remarks. So here's what we do. I think I'm going to take this word which is in our code and this word which is in our code and add them up and see what I get. The sum of these, well, we've proved that 0 is the 0 of the field, and therefore whenever I add 0 to anything, I know what the answer is. I don't know what 1 plus 1 is yet, and I even more don't know what 1 plus 2 is, or 2 plus 1. But that should be in the code. Is there anything that begins with a lot of zeros and then 1, 1? Oh yes, there is. So this number must be 0, and this number must be 3. So we have another theorem. You know, I want to call this theorem 2, really. No, I think I'll have theorem 1. 1 plus 1 equals 0. Well, that's very good. Where am I writing this thing? 1 plus 1 is 0. And now, well, what's wrong with this? Hence, n plus n equals 0 for all n. How did I deduce that? Well, you might think that I multiplied by n. Oh no, I didn't though, because I don't yet know that 1 is the 1 of our field. Well, but I do know that it's not equal to 0, so it has an inverse. So I multiply this by n over 1, and then I deduce that n plus n equals 0 for all n. And hence we have a theorem 2, which the characteristic of our field is, I prefer to say TWO, because it's not clear that 2 means the same thing, so to speak. Hello.
Is it true that if you start with the first thing which appears in a possibility in C3, for example, and add it to the first kind of thing which also appears, as you said, the first one which appears 0, 1, 1, 1, 1, 1, and the first one which appears with different digits is 0, 1, 0, 1, 2. Yeah. And you add them together, you get something which is also the first of its type.
No, that's not necessarily, I mean, without additional meaning, I don't know what this type means and so on. But yes and no, I think is the answer. I mean, the assertion is that the sum of any 2 lexicode words is a lexicode word. And if you ask for the first one of so many digits, and then the first, well, I mean, you can define type in such a way that your statement is true, but then you could also define it in some other ways. So I prefer not to say too much about that. Okay. The characteristic of our field is 2, and so 2 plus 2 is 0, and 3 plus 3 is 0. I'll draw some lines so that I can tell where I am. I didn't do that all that well, but just give me some license and I'll take it. Okay. Now, we also proved that, what was it? Can't can't see it. The 2 plus 1 is 3. In fact, you know, you can prove that addition in the field is commutative even if you don't suppose it, which is rather interesting. But we can prove that this addition is commutative even without supposing it. Well, for instance, we could have added, instead of these two numbers, I could have added them in the other order, and then I'd have proved that 1 plus 2 is 3 as well. Anyway, 1 plus 2 is 3. 2 plus 1 is 3. And now we can start using clever things. We can start being mathematicians for a change. So, for instance, what's 1 plus 3? Well, it's equal to 1 plus 1 plus 2. But fields are associative. I mean, the addition in the field is necessarily associative. So this is 1 plus 1 plus 2. And that's by a theorem we've already proved, 0 plus 2. And that by another theorem we've already proved is 2. So 1 plus 3 is 2. And 3 plus 1 is 2. And then there's a similar proof, 2 plus 3 equals 2 plus 2 plus 1, etc. And you carry on and you'll see that it's 1 because the two 2's cancel. After some use of the associative law. So the first 4 by 4 block of this addition table is already a group. Okay? And now I'm going to prove, you know, somewhere or other I should have had a theorem 3, and I think I like theorem 3 to be 3 equals 2 plus 1. So it explains 3 in terms of smaller numbers. Now, I can prove for you that this sort of pattern continues. Let me sort of say what happened. To get from this square to this square, let me use the coloured chalks that I've been granted here. I'll call this the red implication. The red implication, or the red operation, go up by 4. As I was forming the lexicode at one time, I got to this sort of region, and you'll remember I said it's just as if the integer started at 4. Which means, if you think about it, that when you increase all these numbers by 4, see what I'm doing? I had 2, 3, 0, 1, so I've got 6, 7, 4, 5, and then 7, 6, 5, 4 there. That's the rule for passing from this 4 by 4 block to the next 4 by 4 block. So what's it mean? Well, unfortunately, I can't. Let me call theorem 4. Let me summon theorem 4 into existence. Theorem 4 says 4 plus n equals 4 plus n for n less than 4. Well, I see that there's something sounding tautologous about it. It's not actually a tautology. What I meant by it was that 4 plus n in the new sense is equal to 4 plus n in the old sense that presumably you learnt at school and now know and love, or hate maybe. Well, I'm going to do that. If I put square brackets around any expression, it means evaluate it in the sense of the school book. Perhaps I should go on to say there's theorem 8 as well. 8 plus n equals 8 plus n, or n less than 8, etc. Well, let me, I've just introduced a clever notation, so what I want to say, I want to generalize this. Perhaps I'll rub off these theorems for the moment and we'll have an empty blackboard. If big N is of form 2 to the k, but that's in the schoolbook sense, and little n is less than big N, then big N plus little n equals big N plus little n in the traditional sense. Now, you can prove this most easily by considering not the code C3, but the code C7 or 8. And then you find that, I mean, let me just demonstrate how you do it. You look at this word, which is in the code we're talking about, and then we look also, at that word. And then we look at, is that the one I want? Oh yes, and then I look at 8, 8, 8, 8, 8, 8, 8, 8, and I get that 1, 8, something or other is in the code, and we, on the other hand, we know by what was before the starting at 4 argument, it's now the starting at 8 argument, that this code word is 1, 8, 9, 10, 11, and so on. So that's how you prove theorem 8. Okay, so there's, equally we have, you get this square by copying this one, but increased by 4. And then, in view of the fact that 4 plus 4 is 0, if you go this way and this way, you've increased by 0, which means, let me call this let me use green chalk for this, the green arrow. Green arrow is just copying. And so I've sort of more or less proved that now. One can really prove it quite formally if one wants to. And it tells us that we know the entire addition table. Okay, so we'd better get round to multiplication. Now this addition table, many of you will have met. Computer people know it as XOR, exclusive OR, on the binary expansions. Or, put in other words, write in binary and add without carry. Game players know it as NIM addition, which is rather shorter, and I propose to call it NIM addition. It's a well-known thing, and it arises in the theory of the game of NIM. The multiplication, I believe I was the first ever to discover, and I'm rather proud of it. It's interesting. So let me say, I cannot actually prove that 1 is the 1 of the field. And there's a simple reason for that. Suppose you take every code word and multiply it by 7. No, I'll choose a different number. 6, in the sense of the new multiplication. Then, by the theorem, you know, it isn't a theorem. It isn't a problem, really. It's an axiom. because it's the sort of thing and it says, instead of saying are there, it says there are. Fine. We're taking this as an axiom, we're deducing theorems from it, aren't we? Well, let's push that up there anyway. Let's take 0, 0, 1, 0, 1. Oh, sorry, I was just about to say why I can't prove that 1 is the one of the field. Take the code, multiply every code word by 6. 6 is not 0, so that operation is invertible. When you've done it, you get the same code, exactly. But the unit has changed, so to speak. In other words, if we rename every digit to be 6 times its former self, have 6 times its former meaning, perhaps I should say, then what happens is the new unit of the field changes by a factor of 6. From either 1 to 6 or from 6 to 1, I couldn't care less whichever it is. And so we cannot possibly prove that 1 is the one of the field. Any non-zero number could be chosen to be the one of the field. But in particular, 1 can be chosen to be the one of the field. So that's legal, and so I'm going to make that choice. So this is, what am I doing? This is a definition convention. Number 1 is the one of the field. I won't bother to spell it, write it all out. So that convention, together with some well-known properties, together with the fact that 0 is the 0 of the field, it gives us quite a good start on the multiplication table. Zero is the 0 of the field. 1 is the 1 of the field. The first problem seems to be, what are 2 2's? Okay. Well, let's take a typical code word, and that's the one I'm going to take. That's in C3. And let me multiply it by 3. No, I don't want to multiply by 3, by 2. Multiply it by 2, and I'll get 0, 0. I've proved that 1 is the 1 of the field, so I know all these digits, but I don't know what 2 2's are yet. So what are 2 2's? It's got to be in C3. It's a word beginning zeros and then 2, 0, 2. Oh, there it is, 3. So we have the theorem that 2 times 2 equals 3. That's a bit of a surprise. The time I discovered this fact, I don't think anybody had ever noticed that 2 times 2 is 3 in any sense whatsoever. But 2 times 2 is 3. Fine. And now we can easily prove that 2 times 3 equals 2 times 2 plus 1, which is 2 times 2, which is 3, plus 2 times 1, which is 2, and 3 plus 2 is somewhere up there. 3 plus 2 is 1. So 2 times 3 is 1. Now, indeed, I said it was a field, and you might not have realized that it was a field. The inverse of every non-zero integer is another non-zero integer. 1 over 2, or half, is actually 3. Fine, that's good. let's work out what 3 3s are while we're at it. 3 times 3 is 3 times 2 plus 3 times 1, and 3 2s are, well, they're the same as 2 3s, it's 1, and 3 1s are 3, and 1 plus 3 is 2, so 3 3s are 2. And we notice that these first 4 numbers form a group under multiplication as well as addition. So they form a little field all by themselves. That's the field of order 4, in a sort of slightly unusual guise. Now, I'm going to give you, fortunately I haven't rubbed off the thing that gave the answer to addition. If n is of form 2 to the 2 to the k, and little n is less than big N, then little n times big N equals little n times big N in the school book sense, is actually a theorem which I won't bother to prove for you. Now, I don't want to call this a power of 2, because the powers of 2 in this system are 1, 2, and 3. 2 cubed is 1, so, you know. So these are not powers of 2 in the new sense. I could put power of 2 in square brackets or something, but I prefer to invent an abbreviation. That concept is a 2 power. If n is a 2 power, big N is a 2 power, you add it to any smaller number in the school book way. And I prefer to call this a firmer 2 power. They're the ones such that if you add 1 to them, you get the Fermat numbers, which might perhaps be prime, except that it's all prime. And now, you know how to add and multiply everything. Somebody's leaving, so that probably means I should be stopping.
No,
How much time have I got of it?
another 10 minutes.
Okay, that's fine, that's excellent. You can multiply using this rule. It's not so easy to do. Let me just take some numbers less than 16. Well, perhaps, you know, 2 of you can choose 2 numbers less than 16 for me. Not 0 or 1, it'll be too trivial, you know. Give me a number.
15.
50. Aye. Somebody else give me a number.
70.
7. Okay. So how on earth do we do 15 times 7? Well, 15 is 8, and 4, and 2, and 1. And 7 is 4, and 2. Oh my God, you gave me a complicated. Well, never mind, I'm brave. 4 4s are 6. Oh, perhaps, oh, I didn't say that. I told you what to do, but it says over here at the end of this sentence, but maybe I should not capitalize that B, n times n is 3/2 of n in the school book sense. You know, when I discovered that 4 4s were 6, I was a lot younger than I am now, and it struck me as rather funny. And I lay down on the floor of my college room and waved my arms and legs in the air and giggled for quite some time. 4 4s are 6, friends. Okay. What are 2 4s? 8. What are 2 2s? We've already had that. 3. What are 2 1s? 2. 1 of anything is that same thing. Oh, now we've got a lot to do. 4 2s are 8. 4 1s are 4, because 4 is a firmer 2 power. 8 1s are 8. Okay. What are 8 2s? 8 times 2 is 4 times 2 times 2. 2 because I proved that 8 is 4 times 2. Or really I proved that 4 times 2 is 8, but never mind. And that's 4 times 3, which is 12. So 8 2s are 12. What are 8 4s? Well, that's 2 times 4 times 4. 4 times 4, I just remarked, is 6. 2 times 6, which is 2 times 4 plus 2 times 2, which is 8 plus 3, which is 11. So 8 4s are 11. Good. Oh, that's all very nice, very sensible thing. So now what happens? Well, I can cancel any 2 copies of anything here. And then I can use the fact that 8 plus 4 is 12. So I'll cancel an 8 plus 4 with a 12. I can use the fact that 4 plus 2 is 6. I can use the fact that 11 is 3 plus 8. So 11 and 3 add up to 8. And now I've only got 8 and 2 and 1, which is 11. So whatever you ask, 15 times 7 is 11. Okay. So you can now add and multiply. You may not exactly understand what the hell you're doing. But that's fine. I didn't understand for a long time either. Perhaps I should say I found this in another way. And in the other way, the addition was obvious. Well, I found it actually from the surreal numbers. Some of you may have heard of the surreal numbers. The surreal numbers have a definition of addition and multiplication, and they form a field. And it's an astonishingly large field. It includes the real numbers and all the ordinal numbers and plenty of other things besides. It's meaningful to talk, for instance, of omega, which is the first infinite ordinal, raised to the power of pi, or of the square root of omega and various other things. It's a totally ordered field, and in a sense, it's sort of God's totally ordered field. I was the person who discovered God's wishes in this respect. And I took the definitions of addition and multiplication for the surreal numbers and wondered what they would do in characteristic 2. And so I suspected it was going to be a field or something from the start, but had to prove it, and it was not trivial. And perhaps the best thing I can say to you is that the lexicode theorem is actually a theorem. So, where was it? Oh, I think, you know, we used it, I forgot to call this a definition. But it is a definition, because if you take it as an axiom, it does actually define the addition and multiplication for you. But with that definition, with itself as definition, it becomes a theorem. It really is a theorem. But I rather like the idea of taking you through a journey in which you wonder everything, and then not proving the damn theorem. I'll leave it as an exercise to the reader or the listener. But it's a pretty hard exercise, I warn you, to prove that, especially from this stupid definition I've just given you. It's easy if you do it the right way, but I'm not going to tell you the right way. The lexicode theorem is a theorem, and I'm not going to prove it. I will tell you some interesting things about it. It continues really. It was really transfinite induction that defined this particular code. Well, you can carry on. You can define this addition and multiplication for the ordinal numbers. And then you find funny things. You find, for instance, that the cube of omega, the first infinite ordinal, is the number 2. Since 2 is a cube root of unity. That means omega is a 9th root of unity. Oh well, yeah. I didn't remark that 8 is a 5th root of unity. The other 5th roots of unity, apart from 1, are 10, 13, and 14. What about the ordinal that Cantor, who we'll think of as writing the school book in this case, called omega cubed? Oh, well, that's a cube root of omega. What is that? And omega to the 9th is a cube root of omega cubed. Again, you must hear the square brackets occasionally, even if I don't pronounce them. What about the limit of all of those numbers is the ordinal Cantor called omega to the omega. That's actually a 5th root of 4. Oh, I didn't mention that, of course, 1 over 4 has to exist. We call it a quarter. It's actually equal to 15. I don't know why people are laughing. This is not funny. This is a classification. Well, I don't know. I gave you permission to by saying how I giggled when I first discovered some of these facts. Omega to the omega, it's a 7th root of omega plus 1. Hendrik Lenstra, who's always called Hendrik Lenstra Jr., investigated these higher powers of omega, so to speak, in Cantor's sense. I proved a theorem about them in my little book called On Numbers and Games. And Hendrik Lenstra found out what the first, how can I say it? Various things are square roots, those certain finite integers, cube roots, things like omega, 5th roots, 7th roots, and so on. Lenstra worked out all the way up to 43 what they were the pth roots of, basically. It's non-trivial. He proved a difficult theorem to find this. And he has a theorem evaluating them all to within a finite integer. So, I mean, you know, according to his general theorem, what is it? The 7th power of omega to the omega squared, I think it is, must be of the form omega plus n for some finite n. His general theorem doesn't evaluate what the n is, but you know, in this particular case, n turns out to be 1. And he works out a particular value of n. Yeah, let me tell you a few more theorems. 2 to the 2 is 3. 4 to the 4 is 5. 16 to the 16 is 17. 256 to the 256 is 257. Those are all the Fermat 2 powers, so to speak. If you take each one to the previous one, 4 to the 2 turns out to be 4 plus 2. 16 to the 4 is 16 plus 4 plus 1. 256 to the 16 is 256 plus 16 plus 0 or 1. His theorem doesn't tell you which, but again, he worked out what the first few were.
When you're saying plus, it's the new plus or the traditional plus in brackets?
Both sides, it was the new plus. I mean, it was the new power, and the new plus, which happens to be in those cases the traditional plus. Okay, well, I think it's time for me to shut up. Negative integers. It is the quadratic closure of 2. 2, by the way, according to von Neumann's convention, is the set consisting of 0, 1, and that's a field. It's a field of order 2. When you go to omega to the omega in square brackets, that is the quadratico-cubic closure of 2. Oh no! Oh yes, that's right. When you get to omega to... I think I said something wrong there, but never mind. The next interesting case is omega to the omega to the omega in Cantor's sense. and that is the algebraic closure of 2. So omega to the omega to the omega is the first number that's transcendental over 2. The problem with finding what the next number, next transcendental is something that I posed as a problem in my book. As far as I know, it hasn't been solved. Leinster actually has in some sense discovered the answer, a way of naming the answer. It's quite a large ordinal. It's not large in the sense of proof theory, where certain large ordinals appear as numbers associated with various arithmetical theories and so on. It's not that large, but it's too large to be conveniently nameable in terms of ordinary arithmetic. Leinster found a way of describing it. It's not a theorem. It's based on the assumption that most equations are irreducible. And supposing you've done a lot of cubic extensions, how many have you done? Well, you've done just as many as there are cubic equations, basically, because the number that are reducible is small compared to the total number, and it won't affect the answer. But, that's an elite, that isn't a proof, but it strongly suggests what the number is. And I think it would be very hard to prove it.
You take all the ordinals, that's closed? Algebraic?
Yes, the entire set of ordinals forms a field.
Algebraically closed.
It's algebraically closed, yes. It's analogous to the surreal numbers. If you stop the construction at certain nice ordinals, it will be a field or an algebraically closed field or something. There are some wonderful theorems, the simplicity theorems, that I state and prove in my book. Suppose you've got all the ordinals below some point, and you've filled out the addition table and multiplication table, as long as the answers are below this point that we're talking about. And then you take any lexicographically earliest pair of numbers that haven't yet received a sum, then the next, for all of them, the sum is that next ordinal. Okay. And then, let me say that a slightly different way. If I consider all the ordinals less than a number I'll call delta, and if there is some pair of them whose sum isn't less than delta, you take a lexicographically earliest such pair. Every lexicographically earliest such pair has some delta. And then suppose all the sums have been defined and are less than delta, that's what it means, but there is some product which hasn't yet been defined. Then you take a lexicographically earliest product that's not yet been filled in. All such lexicographically earliest products have value delta. If it were not a field automatically, and it isn't after some time, if it's closed under addition and multiplication but not under inversion, reciprocation, then the next ordinal is the reciprocal of the lexicographically earliest thing that hasn't yet got one. Okay, so otherwise it's a field. If it's not algebraically closed, the next ordinal is the root of the lexicographically earliest polynomial that has not yet received a root. And then if it is algebraically closed, the next ordinal, there's no choice, it's got to be transcendental in the previous ones. That's why omega cubed equals 2. Because at omega we're quadratically closed. So omega must satisfy a cubic equation. What's the first cubic equation? X cubed equals 0. That's got a root. What's the next cubic equation? X cubed equals 1. That's got a root. What's the next equation? It's x cubed equals 2. Now, x cubed equals 2, oh my God. Has that received a root yet? Is there any finite number whose cube is 2? Well, the answer is no, because all the finite numbers lie in fields of order, I'm talking without square brackets now, 2 to the 2 to the n, and 3 does not divide 2 to the 2 to the n minus 1 for any n, and therefore it hasn't received a root. So x cubed equals 2. Sorry, omega cubed equals 2. That's the way it goes. But those simplicity theorems I just stated are not obvious, and I prove them in the appendix to part 0 of my book on numbers and games. And as I say, they need proof. Ledstra discovered a bug in that, which I corrected in the later edition, but it's not really serious. It doesn't affect the understanding. I can't remember what it was.
Can you define exponentiation?
Now, exponentiation is rather funny. It's a good question. I call these things nimbers rather than numbers, in a way, when I'm being serious. Because, you know, there's one of them for each number, but they're not the same. The addition and multiplication aren't the same. And in the theory of games, both kinds exist. Now, when I say 2 cubed, for instance, is 1, or omega cubed is 2, let's take omega cubed is 2. The omega in that is a number, but the 3 is a number. And you can't define exponentiation in the nimber on nimber sense, so to speak, because exponentiation would give an isomorphism, I would say, but, well, roughly an isomorphism between the multiplicative group and the additive group, a homomorphism of some kind anyway. And the additive group is just C2 cross C2 cross C2 and so on. The multiplicative group contains elements of order 3 and so on. So it's just not sensible to try and define nimber to the nimber in such a way that you get the obvious set of holes.
From nimber to the nimber. Actually, in the reals, in order to define number to the number, you just have to know what is e to the number.
Yeah. By the way, in surreal numbers, this problem happens also. Exponentiation is rather more subtle, and but I'm not talking about the surreal numbers. Perhaps I shouldn't go on. But I mean, there is an analogous question there, and the answer is, as I said, subtle. So let me not discuss it. Just point it out.
So what brought your attention in the first place to these codes with a certain minimum distance between the words?
Yes. Ledstra is the answer, I think. I tried to find a game whose solution involved nim multiplication. And in my book I defined a rather stupid game that just sort of forced it in. Ledstra pointed out that there was a notion of products of certain games, and that this gives rise, how can I say it? Whenever you have a game of nim-like type, the sum of two games, each game gets associated to a nimber, its nim value, it's equivalent to a nim heap, and the sum of two games is associated with the sum of the two nimbers. That's Bouton's, no, not Bouton's theory, this is the Grundy-Sprague theory, which is an extension of Bouton's theory of the game of nim. Ledstra, but the point is, then there's a winning code. You say how many things you've got, how many copies you've got of each position in the game, and that's a code word. That's a word, and you put it in the code if it's a safe position to move to. was a good position to move to. And so the code arises naturally from limbs. Now I'm going to tell a story. After this conference on games that I was talking about, I had to give the last but one plenary lecture at the Zurich International Congress. The last lecture was Andrew Wiles's lecture. At that time he discovered the bug, and the sort of message of his lecture was that the US cavalry were on the way. The bug would be cured, you know. Everybody, you can imagine, was in the lecture room to hear this. And I was in the last room, same room in the hour before. So I got all his audience because, of course, they were all keen to get seats. So I was talking to about 4,000 people. I don't know whether I mentioned, I had been intensely depressed and attempted suicide the year before, was still in a rather delicate state, but I'd just given this talk at this game theory conference. And I determined that I would give exactly the same talk at the International Congress. But unfortunately, my title was The Last 4 Years in Sphere Packing. Or, no, it was actually Sphere Packing something, oh God, Sphere Packing, but I can't remember what it was. I wrote, this was on one of these big overhead projectors standing there for half an hour before the talk. I crept up to it and wrote, "and greed" at the bottom of it, because it's a greedy algorithm that's used here. And then, you know, everything happened wonderfully. Namely, I was very worried about this talk. On the way to the Congress Hall, I passed a drugstore, and there was a basket of balls about this size of expanded polystyrene. They're very squashy. Fine. So I went and bought the entire stock. And then when I got to the Congress Hall, they were still serving coffee in tiny paper cups. I found I could squeeze 3 of these balls into one paper cup. And then I was also wearing a jacket, a white jacket, off-white, because I'd worn it for quite some time. It had rather large pockets, and I stuffed the pockets with these paper cups with spheres. And then I stood up and said, you know, here I am. I said, I only slept an hour last night. If there's something wrong with me, I always say what it is. Get the audience on your side. That's all. And I said, here I am. I haven't prepared my talk, you know. Here I am on stage at an international congress, and I'm going to wing it. And then I said, suppose you have a number of spheres to be packed into n-dimensional Euclidean space. Well, if n is 0, this is pretty easy. The space only has 1 point. It's a bit hard to see it. So I'll inflate it to a ball, you know, and I pulled a ball out of my pocket that was obviously not big enough to contain that ball, to have contained it. So I put it on the table, and I said, that's done, you know, 0 dimensions. And now in 1 dimension, we'll need more balls. You know, I pulled another ball out of the pocket and so on, and I got a line of 4 balls. And at this point, I'm afraid I told a lie. I said, but now, I haven't any more balls, so you'll just have to pretend that 4 is equal to infinity. They're all in a line. It's a sort of kebab. If I had more balls, oh yes, I do actually. We could stack a number of these kebabs together and get what I'll call a waffle, which is a 2-dimensional way of packing spheres. And now, oh yes, I pulled some more balls out. In the end, I built up a sort of quite big pyramid of balls on the lectern. And then I did the audacious thing. I said, now I'm going to change subject a little bit. And some of you won't recognise the connection with sphere packing. What I didn't say was that most of them wouldn't recognise the connection with sphere packing even after the lecture finished. Because there wasn't really much connection with sphere packing. It was a very tenuous one. So then I gave this lecture I've just given you, which was, of course, a riotous success. And it always has been ever since, I think. So whenever, you know, I find I've accidentally given a title which is a bit boring, you know, I can always turn to this one. Then at the end of the lecture, I threw these balls out into the room, and people scrambled, people in the first 10 And I met Marston Conda just perhaps 2 months ago, and he said, I have one of those. So that's it. And then Fadea wrote a description of the Congress for his Russian colleagues who couldn't get there. And he said, this is what a talk ought to be like, basically, single out people. And that, of course, cheered me up no end. And it's from that date that I date my coming alive again after attempting suicide, and damn nearly succeeding. You know these 2 numbers that they give you after they've read your blood pressure and everything? My reading at one point was 20/0. Yeah, 20 meant 20 is 20. It's very, very low. You don't
This is in the new arithmetic or the old arithmetic?
Zero meant they could pick up no signal, and I survived somehow. And then I went 6 months later or something to the International Congress, and then I really came alive. And there's another thing which I oughtn't to tell you, but I will. I was with a girlfriend, Penny, and Penny's atrocious behaviour at the party rounded off that conference beautifully. That's another story.
Okay, so we promised the undergrads we'd get some time to ask some questions without the professors again. So you'll have some